Alright, welcome to the second week here as we continue on the refraction and lenses chapter. Today I'm going to make a couple different clips. This first one will just be on the convex lenses and the real images that they produce. Then I'll go into one where there's convex and virtual images, and then we'll have one just on the concave lenses. So this is very similar to the curved mirrors part that we had, right before the break. So some of this will look very familiar, and they are related to each other. Alright. So as we look at a lens, it's usually made out of glass, or it could be some other transparent material, but it is going to focus light and form an image. These images are going to be real, or they could be virtual. For the most part, we're going to deal with two types of lenses. The convex lens, which is curved on both sides, which causes parallel light to focus in a certain point. This would be like your magnifying glass that you may be familiar with. Notice it is thicker in the middle, and because of that, as light comes in there, it is going to cause the lens to bend down and then end up going through that focal point, which we'll talk about later on. The other type of lens is the concave lens. This is where it's thinner in the middle. Light that goes through this is going to diverge or spread out as it goes through the lens. This will produce only a virtual image. We'll talk about that in a whole nother video later on. Okay, now in terms of some math, there's going to be a thin lens equation which is going to look exactly like the equation that we used for the curved mirrors, and that is 1 over f equals 1 over di plus 1 over do. Remember that f is the focal length, in this case of the lens, di is the distance of the image from the lens, and do is the distance to the object, such as a light source that is from the lens. Alright, there's also the magnification equation. Once again, this is the same as the spherical mirrors. Magnification is defined as the image height over the image, or the object height, or you could say the distance image divided by the distance object. Once again, this is just a summary of all the different things that can occur. There are 3 different examples that we'll talk about with convex lens. It's all based upon where the object is related to the focal length. And then there's only one scenario with the concave, just like what we had with the mirrors on there as well. Okay, and so this, you could hit pause, you could look at all these different things. I'm not going to go over each one right now. Maybe I'll come back to this later on. The focal length, when we look at the lens, will depend on the shape of the lens, as well as what the material is made up of, whether it's glass or plastic. The focal length of a concave lens can be negative, and the image will be negative, but we'll get into that another time. In terms of real versus virtual images, real would always be on the other side of the lens, whereas when it was a real mirror, real image with the curved mirrors, it was on the same side as the mirror. So you'll see this here coming up in a diagram. So once again, concave lenses will only produce virtual images, and then the convex lenses, which are thicker in the middle, this is your magnifying glass, they can produce real images on a screen, or they can produce virtual images. Alright, now as we start to look at convex lenses in more detail, first of all we have here is looking at parallel light, for example, from the sun. So if you've ever taken that magnifying glass and tried to burn something, this is what's going on there. Okay, so you have the parallel light from the sun, and all those parallel beams will focus on one certain point, which we call the focal point. This is why you don't want to look at the sun, because then all that sunlight will focus on the back of your eye and cause your eye to burn, just like you would that leaf or the ant with a magnifying glass. Alright, real quick, let me pull up this video.
In this animation, rays are traced from an object being viewed from a convex lens. For the purpose of locating the image, you only need to use two rays. Ray 1 is parallel to the principal axis. It refracts and passes through F on the other side of the lens.
Okay, so I'm not sure if you're hearing the video or not. I have a feeling that you are not. But just in case, just so you can see, when we draw this, we start with a parallel line from our object, and as it hits the lens, it bends twice. When we do this, you can just show it bending once, but it'll go parallel, and then it'll bend through the focal point on the opposite side. Now, as I didn't state earlier, there are actually two focal points, one on each side of that lens. So there is ray 1.
Ray 2 passes through F on its way to the lens. After refraction, its path is parallel to the principal axis.
Okay, so there is ray 2. Ray 2, you aim for the focal point. When you hit the lens, you come out parallel. So where those two cross then is where your image would be located.
The two rays intersect at a point beyond F and locate the image. Rays selected from other points on the object converge at corresponding points to form the complete image. Note that this is a real image that is inverted and smaller compared to the object.
Okay, so based on where it started, meaning outside twice the focal length, you can see how this image would be upside down and it would be smaller. And in this case, it is real.
If a refracted ray is reversed in direction, it will follow its original path in the reverse direction. This means that the image and object may be interchanged by changing the direction of the rays.
Okay, so this is just showing another example where instead of being on the left like we always use, it's starting on the right. And so it started upside down, and you still use the same rays. The first ray goes through the focal point on the same side. It comes out parallel. The second ray starts parallel and then goes through an angle through the focal point. Where those two crossed is our new image. And in this scenario, we get an inverted compared to our original, and it is real. And it's also much larger because it's between the focal point and twice the focal point.
Let us consider that the object is at a distance of 15 centimeters from the right side of the lens. If the path of light through the lens is reversed, the new image, located 30 centimeters from the left side of the lens, is a real image that is inverted and larger compared to the object. If the object is placed at twice the focal length from the lens at the point 2F, the image also is found at 2F.
Okay, so just like the mirrors, if you put your object at twice the focal point, the image will show up at twice the focal point, and they will be the exact same size. I'll do some examples of this showing you the math later on.
Because of symmetry, the image and object have the same size. Thus, you can conclude that if an object is more than twice the focal length from the lens, the image is smaller than the object. If the object is between F and 2F, then the image is larger than the object.
Okay, so hopefully you kind of could follow along with that. You could read the subtitles if you could not hear the computer going through that. So I'm going to stop right now and do an example on another video.